In this example, I want to apply what we already know about the work-kinetic energy theorem to see if we can derive some sort of expression that helps us understand better the law of conservation of energy. So there's a hypothetical case where a block of mass m is initially in motion, sliding across an inclined plane angled at an angle theta. And there's a spring whose relaxed length is shown, but it doesn't start out at its relaxed length. There's a locking mechanism or a ratchet that has the spring already partially compressed. In the final state, the block will have displaced this far up the incline, and now the spring is in an even more compressed state, and the block is perhaps still in motion. So we haven't reached the maximum compression of the spring yet. So based on the work-kinetic energy theorem, let's see if we can derive an expression that helps us determine the ways in which energy have been converted. So here's the diagram repeated. So instead of stating initial and final, we just draw the block in position A, which is the initial position, and B, the final position. Okay, so we're assuming there's no friction, and we'll start with the work-kinetic energy theorem that says the net work being done on the block is equal to the block's change in kinetic energy. Okay, so what forces are involved on the block? We make a free body diagram. Once it makes contact with the spring, then there's a normal force. There's the force of gravity. The spring pushes down the incline. Call that F subscript S. And that's it, right? There's velocity pointing up the incline, but velocity is not a force. There's no friction, like we said. So that's it. We also know that normal force won't do any work because as a vector it points perpendicular to the displacement. So the net amount of work is going to be the work done by the spring plus the work done by gravity. And that's equal to the final kinetic energy minus the initial kinetic energy. Now if we keep this generic, work done by the spring is the integral of the force of the spring dot product with the displacement of the spring. And the work done by gravity is the integral of the force of gravity dot product with displacement along the incline. That's equal to 1/2 m times final velocity squared minus 1/2 m times initial velocity squared. Okay, so let's make sure we have our reference system clear of how we're measuring x, the compression of the spring. So this represents the relaxed length of the spring. So we'll say that's the equilibrium position, or in other words, the point where x would be equal to 0. So the spring had started out already when the block first makes contact with it with some amount of compression we'll call x naught, and by the time it reaches position B, the spring has a compression that we'll label as x. So this force exerted by the spring is only occurring from initial position of x naught to a final position of x. So our limits of integration are from x initial to x final, and the force exerted by the spring has a magnitude of kx. And because the force exerted by the spring points down the incline, but the displacement points up the incline, then the angle between force and displacement is 180 degrees. Okay, now as far as the force of gravity goes, we know its magnitude is mg. Well, wait a minute, we can simplify this. How about instead of picturing gravity as pointing straight down, let's break it into its components. So there's a component of gravity, mg cosine theta, that points perpendicular to the incline, and therefore perpendicular to the displacement. And there's the other component of gravity, mg sine theta, parallel to the incline and pointing opposite the displacement vector. So we know that this component of the force of gravity does no work in the same way that the normal force is doing no work. So we can consider the work done by gravity as the work done by the component of gravity, mg sine theta. And for what distance now is that force taking place? Well, gravity doesn't begin to engage the moment the block makes contact with the spring. Gravity is acting on the object during its entire displacement of the incline. So we'll set up a reference system here where s equals 0 at the bottom of the incline. So the block starts out with some initial position s naught and ends up having traveled some final displacement s. So from s naught to s, anyway, so far I've just calculated the force. Now we need displacement. And once again, this component of the force of gravity is down the incline, displacement points up the incline, so there's another cosine of 180 degrees, and that's equal to, we can just copy and paste all of this. Okay, step 5. Well, what do we get if we evaluate here? The cosine 180 just gives us a -1. Same here, cosine of 180 gives us a negative sign. So we're going to have negative k, negative 1/2 k x squared minus negative 1/2 k x initial squared plus negative mg sine theta s minus negative mg sine theta s naught, all equals change in kinetic energy. So let's see, double negative here, right? Negative, negative, so we can say this is 1/2 k x naught squared minus 1/2 k x squared. And we again have a double negative, 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 so we have plus mg s naught sine theta minus mg s sine theta equals change in kinetic energy. Now notice something. S naught sine theta. Let's see. So this displacement represents S naught. The incline is, let's see. I guess S naught times sine theta, if we're picturing a right triangle, if S naught is the hypotenuse of that right triangle, then S naught times sine theta is the opposite side in that right triangle, which we would probably refer to simply as H naught, right? If the bottom of the incline is H equals 0, then we can call this H naught. And in the same vein, if we look at this right triangle, S is the length of the hypotenuse, so S times sine theta will be nothing more than the final height. So there's an initial height of H naught and a final height of H. So we can replace this with H naught and replace this with H. 1/2 k x naught squared plus mg h naught minus 1/2 k x squared minus mgh equals 1/2 mv squared minus 1/2 mv initial squared. I know you're hanging in there. This is a long derivation, but we're almost there. So let's just get these quantities with a negative sign and bring them to the other side of the equation, right? In other words, we're going to add 1/2 kx squared and mgh to both sides of the equation. In the same way, we'll add a 1/2 mv naught squared. In other words, we will have 1/2 k x initial squared plus mgh initial. And then we bring this to the other side of the equation, plus 1/2 mv initial squared is equal to, this gets brought to the other side of the equation, 1/2 k x final squared plus, this goes to the other side of the equation, mgh, and we're still left with plus 1/2 mv final squared. So do you see what we really have here? This is just a way of saying the initial elastic potential energy plus the initial gravitational potential energy plus the initial kinetic energy is equal to the final elastic potential energy plus the final gravitational potential energy plus the final kinetic energy. The combination of all these forms of mechanical energy is equal to the combination of all those forms of energy in the final state. That doesn't mean any one type of energy remains constant. They're all converted, but the total sum of energy remains the same before and after. So what we end up with is a statement that says the initial mechanical energy is equal to the final mechanical energy. This is the law of conservation of energy. And when written in the form of equation number 8, becomes a powerful tool for solving problems that might otherwise be more challenging if we were simply to rely on what we know about Newton's laws and kinematics. So I'm going to rewrite that expression one more time. For an object that's only being worked on by conservative forces such as ideal springs and gravity, then the initial kinetic energy plus the initial gravitational potential energy plus any initial elastic potential energy is equal to the final kinetic energy plus the final gravitational potential energy plus the final elastic potential energy. Now there may be some cases when we apply this equation where we can let some of these quantities be equal to 0. For example, what if we were just simply trying to figure out how fast an object hits the ground when released from rest from a height of h. So we'll say the floor is h equals 0, the object is dropped from a height of h, and we're trying to find how fast it travels when it hits the ground. Now if we were to use Newton's laws, we'd say that the force is equal to mg, so ma is equal to mg. Mass cancels out, which is why all objects accelerate at the same rate. It's true that a heavier object feels a bigger force of gravity, but it also has that much more inertia. So all objects in the absence of air resistance should fall at the same rate. So if the acceleration is acceleration due to gravity, then we use kinematics. We say v final squared equals v initial squared plus 2 times acceleration times displacement. The initial velocity is 0 if it's released from rest. The acceleration is g, and the displacement is h. So we find that the final velocity is the square root of 2gh. Okay, that's how we've solved this problem in the past. In this case, we can recognize, well, there is no spring involved, so there's no initial or final elastic potential energy to solve for. In the end, because the block is going to hit the ground, it's going to reach the height at which its final gravitational potential energy would be 0. So we can cancel that out. Its initial kinetic energy is also equal to 0 because it was released at rest. So we just have an equation that says mgh initial equals 1/2 mv final squared. mgh equals 1/2 mv squared. Mass cancels out. We multiply both sides of the equation by 2, take the square root of both sides, and what do we find? V is the square root of 2gh. Okay, so it should be satisfying to see that what we know from Newton's laws in kinematics agrees with this equation that represents the law of conservation of energy. So we're going to apply this equation in several examples as we work through the remainder of this unit of study. Thanks for watching.